In this video, we're going to talk about measuring pressure. So one of the devices we use to do that is a manometer. You might be more familiar with a barometer for atmospheric pressure. It's a similar idea, but we're going to talk about where pressure measurements are coming from. One of the tenets of gas theory is that the particles are all bouncing around, hitting other things and bouncing into the walls. If you look at any specific sample of gas, for all intents and purposes, each point in there is bouncing kind of in all directions. It's pushing against all the other things, and on average, it's just shoving into everything equal from all directions. If you ever have equal forces pushing on something, it doesn't really go anywhere. Say you had a tall bookshelf, and you stood in front of it and you pushed. If it was just you pushing on it, it would tip over. But if you have someone on the other side, and they're pushing, well, they push the opposite direction. Your two forces cancel each other out, and it doesn't tip over. This is the same idea with pressures. If you have opposite forces that are equal, there's no change. But if one of those forces is bigger, it's going to push the material in that direction. And so, while two equal drawings here work just fine, if you have someone smaller, well, they're not going to exert nearly as much counterforce, and it's probably still going to tip over, and then you have a legal issue on your hands. Right? This is kind of what's going on with pressure. The gases, any sample of gas is pressing on whatever it's near, equally in all directions. So this is pressing all over, this is pressing all over, but it's pressing down. This gas is pressing up and down, and the ones at the surface here are bouncing into the water. The net result is this outside air is pressing down with some force on the water. Now I'm going to use for this video our standard 1.035 kilograms per centimeter squared. We're going to pretend that this tube is 1 centimeter squared in circumference area. So we're exerting a pressure down, and as long as my tank was open to air originally before I go and connect everything, so there was air outside, and I got inside, we're exerting exactly the same force on this side. It's all coming from the atmosphere. But if I hook it up to a vacuum device, connect it, and I start pulling out some of that gas, well, if I suddenly have less gas inside, I have a smaller force. There's less stuff hitting the surface, so there's less weight pressing down. And remember that our pressure is a weight over an area. And so over my area surface on the inside, I just have less gas. Well, the net result is I'm going to push things. And so the liquid will start to decrease on one side and increase on the other. By pushing harder on one side, I move the liquid that's in between, and I push it in the direction the greater force wants it to go. That's kind of how a straw works. You pull a little vacuum on one side of the straw, the liquid flows up the straw. But if you've ever used a straw, it doesn't run continuously. Eventually, the liquid stops going up the straw. You have to keep pulling, or you have to keep applying more suction to make it keep flowing. So why does it stop? If our pressures are just different now, what's going on? Well, remember our pressure unit. The gas outside, we assume is standard atmosphere for this problem, but any matter pressing down has a weight over that area. And so over here in our tube, well, I have liquid between this height and this height. My liquids aren't equal. If you ever have a container, the liquid always flows to fill your container as a flat surface. It'll fill from the bottom and it makes a flat surface as it fills. That's because if any one part of the water was higher, well, there'd be more weight on this side pressing down. As it moves through the container, that would result in pushing the other side up. Liquids will always balance until they're equal. Right now, I have a pressure pushing down that is much greater than the pressure on this side. My liquids can also exert a pressure. If you've ever been diving, you've felt it. It presses on your ears, it makes your body chest compress a little bit as you dive deeper. There's still a weight of material pressing down. Let's say for a moment that this height difference is 10 centimeters. What that means is there's more weight of water on one side than the other, but that difference is only whatever water is in that 10 centimeters. So I have a tube that is 10 centimeters tall, and what we said earlier, I'm going to correct that. We said it was 1 inch. Let's call it a centimeter squared for its area, since we're working in metric. And it's 1 centimeter squared for its base. All of that water weight is pressing down on 1 centimeter squared. Just like gas in our column when we were doing PSI in a previous video. We talked about all the gas inside it pressing down on that 1 inch squared when we were calculating 14.7 pounds per inch squared, which was the weight of the 1 atmosphere. Well, if I'm doing it with water, 10 centimeter tall column, each single centimeter. So here's 1 centimeter up, here's another, here's another. Each centimeter tall is going to be a circle that goes up to another circle, and it's filled with water. 1 centimeter squared at base, going up 1 centimeter tall, is 1 centimeter cubed. Basically, we can cut this column into a bunch of little circles. Each of them 1 centimeter cubed in volume, which means that whole section right here, for our calculations, that extra 10 centimeter tall section of water, because our tube is 1 centimeter squared in its cross-sectional area, gives us a total of just 10 centimeters cubed. Each one little section was 1 centimeter cubed, so this is a total of 10 centimeters cubed for our example. If we'd had a wider tube, then I'd have more centimeters. We used a nice simple one that was 1 centimeter squared for area. What this tells us, though, is it lets us find the weight. What is the amount of water in here? Well, water is 1 gram per milliliter, which is 1 gram per centimeter cubed. If I have 10 centimeters cubed, that's going to be 10 grams of water, or 0.010 kilograms of H2O. That blue arrow, that little bit of extra pressure, we can actually find it. If we know the weight of the water pressing down and the area of the tube, we can find what the pressure it exerts is. 0.010 kilograms per centimeter squared. It's not a lot in this example, but that is the little bit of extra that it needs in order to cancel out the extra pressure from outside. What this tells us is that the gas pressure on the inside must be that much less. Clear a little of our drawing. Effectively, I still have some gas pressure, so inside gas, and I have some liquid pressure. Well, the inside and the liquid, if my liquid is no longer rising, it must equal the outside. This is why the liquid in your straw stops rising after a moment. You pull a little vacuum on the straw, causing the inside pressure from your mouth to be a little lower than the outside. The outside pushes that liquid up the straw until the extra weight of the liquid, due to its height, matches the lost pressure when you pulled suction. We can even calculate it if we wanted. We know the outside is, well, in kilograms, 1.035 kilograms per centimeter squared. And we know the liquid is 0.010 kilograms per centimeter squared. If they have to be equal, rearrange, what we'll find is that our inside has to be the difference, 1.025 kilograms per centimeter squared. We didn't really remove that much pressure, but we also didn't raise water very high. This is how we actually go about measuring pressure changes, though. When you want to know whether you have less pressure inside or more by pushing the liquid up the other side of the container, you look at that height difference in your liquid, determine the pressure from the liquid, and say, well, if I'm no longer moving, my inside total and my outside total must be equal. Do the calculations, you can figure out what your inside must be compared to the outside. Where we see this most often with manometers is honestly in things like millimeters of mercury, because that is literally where this unit comes from. In millimeters of mercury, it's a slightly different process. We have an open tube on bottom that goes up to a sealed top. We have a big bowl of mercury, so Hg, and we pull a vacuum on the inside of the tube. The result is there's no pressure on the inside. So there's a bunch of gas on the outside. It's all pressing down, which forces the liquid to push it up into the tube. There's no resistance inside the tube. And so the liquid starts to go up. But as that happens, well, now I'm developing a little bit of resistance pressure. As the liquid goes up, I develop even more liquid resistant pressure. And eventually, our liquid won't go any higher. At that point, what we will find is that our outside pressure must match the pressure from that liquid. Well, you need a good deal of height to do this with water. 14.7 pounds per square inch is the outside pressure from gas. To counter that, you need 14.7 pounds per square inch of material weight. For water, that's about 32 feet tall before you reach that weight. But for mercury, that's about 760 millimeters. You need substantially less height of mercury because it is significantly more dense. Mercury, on a volume-to-volume basis, is many, many times heavier than water. So you get the same opposing weight with far less height. If you have 1 atmosphere on the outside, what height of mercury would have the exact same opposing force was 760 millimeters of height. And this is where the millimeters of mercury, this is where the unit actually comes from. It's literally measuring the height mercury would go up the tube. Because that is the height where the weight of mercury pressing down on the area of the tube is equal to the weight of the atmosphere pressing down on a similar area of the pool of mercury at the bottom of the bowl. Key to pressure measurements in this case with these little devices are the opposing forces. How much pressure is in each direction? From multiple sources, just add them together. Total pressure from the inside, total pressure from the outside.